Okay.
Oh, it says I am screen share. All right. Let's hope.
Yep. And you are recording.
Okay. So we're going to talk about reactance, impedance, resonant circuits, inductance, and transformers. And reactance is basically the way capacitors and inductors behave with alternating current as opposed to direct current. And we define reactance as, and this is a test question, the opposition to AC current flow by either inductance or capacitance. And if you remember, we define resistance as the opposition to current flow. It doesn't matter whether it's direct current or alternating current. Resistance.
Say it one more time. Say it, well, the previous one.
Resistance or reactance?
Resistance.
Resistance is the opposition to current flow.
Any flow.
Any
Direct
flow,
or AC.
independent
Got
of
it.
frequency.
Thank you. Excellent.
Reactance is the opposition
To AC
that's
flow.
frequency dependent.
Gotcha.
Okay, and it will behave differently with an inductor or capacitor.
Okay.
One will have a plus 90-degree phase shift, and the other will have a negative 90-degree phase shift. And we'll talk about Eli the Iceman when we get there, which is a little way to remember that. So capacitive reactance, and we usually represent that as an X sub C, and inductive reactance with X sub L. So in capacitive reactance, its opposition is inversely proportional to the frequency. In other words, the higher the frequency, the less opposition, or I can't really say resistance, but it's effectively a resistance that's frequency dependent. Whereas inductive reactance is directly proportional to the frequency. In other words, as the frequency increases, the opposition to current flow increases. So one promotes current flow with high frequency, the other one tries to block it. And that's very important for a lot of circuits. So if we look at capacitive reactance, and the formula is the reciprocal of 2 pi f times the capacitance. So it's omega c, if you remember that omega was 2 pi f. So it's the reciprocal, and that's what gives it, as the frequency increases, the reactance is going to decrease because it's a reciprocal function. You're dividing the larger f is, the smaller the result's going to be. And it actually causes a phase shift. So we use the little phrase Eli the Iceman to help remember that. And the way this one works is E is the electromagnetic force or voltage, and L is in an inductor, and I is the current, which means the voltage in an inductor leads the current. When we look at the capacitor, it says that the current in the capacitor leads the voltage. So what that means, like in the capacitor, when we apply a voltage, like in this little circuit, initially I'm going to have high current flow. It's only going to be limited by whatever series resistance there is in the circuit. If I applied it directly to the capacitor, I'd get an infinite current initially. And as that capacitor charges, the current's going to decrease until after, and we talked about 5 time constants, it's going to be up at 95%. charge, and the current is going to be at around 5% of what it was. When we calculate this reactance, X sub C, we plot it on the complex plane, and it will be negative. Now, I don't know, I guess we didn't mention, if you plot real numbers on a horizontal axis, and we call that the real axis, we plot imaginary numbers or complex numbers on the vertical axis. And we plot capacitive reactance as a negative on that imaginary axis, and we'll do inductive reactance on the positive side. And it might be a little clearer later on when I can show you the plots, when we talk about impedance, which is the sum of resistance and reactance, vector sum. So inductive reactance is going to be omega L, or 2 pi FL. So you see that it's directly proportional. So the larger L, or the larger F is, the larger the reactance is going to be. So it increases with frequency, whereas capacitive reactance decreases with frequency. And in Eli the Iceman, okay, the voltage in the inductor leads the current. It means initially on the inductor, we apply a voltage to it. It's going to essentially apply an equivalent resisting voltage, and the current will be 0. Over time, the current will increase and the voltage will drop, just the inverse of the capacitor. So after about 5 time constants, we're going to have 95% of our current flow, and the inductor will be up here as a 0. But when we talk about the, can't see on this plot. Did I plot frequency? Yes. In this frequency plot, we saw that the inductor appeared to have 0 resistance or reactance initially at very low frequencies. And as the frequency increases, then it sort of exponentially, and this is a log plot, goes up to, well, it would approach infinity. Whereas if we go back on the capacitive one, this is also frequency down here. We see that it has a very high reactance at a low frequency. And I think this is, looks like that's 1 hertz. Or maybe it's a kilohertz. Yeah, it's kilohertz. And it goes down essentially to 0 at the higher frequencies. So that's the basic thing you need to remember, is that the inductive reactance increases with frequency and the capacitive reactance decreases with frequency. And I think there's exam questions about that. May not be worded that way, but that's what you need to remember. So if we get an example, what's the reactance of a 1 microfarad capacitor at 10 megahertz? So we use the formula. Capacitive reactance is reciprocal of 2 pi FC. And we plug in 2 pi, which is 6.28. times 10 to the 7th, which would be 10 megahertz. And a 1 microfarad capacitor is going to be 10 to the minus 6th. So the answer comes out 0.0159, or very low resistance or reactance. If we calculate a 1 microhenry inductor at 10 megahertz, it's going to come out to 62.8 ohms. So you can see the difference between the capacitive and inductive reactances for the same frequency and sort of conjugate values of capacitance and inductance. So the main thing to remember as far as exams are concerned is reactance is the opposition to AC current by inductance or capacitance. You'll need to remember the reactance formulas. There's good chance there's a math question about those, like the ones I showed, where capacitive reactance is the reciprocal of 1 over, or reciprocal 2 pi f times the capacitance. Inductive reactance is just 2 pi f times the inductance. And remember Eli the Iceman, that voltage in the inductor leads the current, current in the capacitor leads the voltage.
As I remember, a long time ago, it also had questions in there showing you what the formula is. And then later on, they're gonna ask you, on a different question, you're gonna have to use that formula which they already showed you.
Oh, okay. Well, that's nice of them.
Huh?
That's nice of them.
Yeah.
I don't remember if they did that or not. I haven't gone through the tech exam in a while. Most of the onlines I've been doing are extras.
I haven't.
General.
This is what I remember from.
Yeah.
Giving tests before. I still got copies of them someplace.
Okay, so impedance. Impedance is also the opposition to the flow of alternating current. It turns out it's the vector sum of resistance and reactance. So we know that resistance is frequency independent, but reactance is frequency dependent. So that's where we get the vector, because we plot the reactance vertically on the imaginary axis. So that gives us a vector, assuming that reactance is other than 0. So the impedance, let me turn my hand over here. Whatever resistance R is, okay, I plot the, and this isn't my chart, and this is not right. It's actually the sum of the inductive and capacitive reactances, and capacity one's going to be negative. So if you plug the negative in there, it's going to give you instead of the difference between the two, it would give you the sum. So it's going to be the difference between capacitive and inductive reactance. And I think that's what they tried to represent, but it really should have been plus X sub C. So the impedance vector is going to be the magnitude of the hypotenuse of that triangle. And we use old Pythagorean's theorem. So and we represent impedance with Z. So Z is equal to R plus or minus JX. And I'll talk about J in a minute. So the hypotenuse is going to be equal to the square root of the sum of the squares of those opposite sides. So you square the resistance, you square the reactance equivalent, and take the square root of the sum of those, and that will give you the length of the impedance vector.
Like 3, 4, 5.
In this case, it could be a 3, 4, 5. Now, you probably haven't seen the J before. And in mathematics, a little interesting thing came up about -1, and what is its square root? So, because nobody knew, okay, they called it I. Well, in electrical engineering, because we use I for current, we use J. So it's, if you see some math stuff with I's in it, it's the same thing as J in electronic or electrical engineering. So that's how we represent things on the complex plane or the imaginary axis. With that J, which is the square root of -1. So here, the capacitor is going to be represented on the negative complex axis or imaginary axis, and the inductor is going to be on the positive imaginary axis. So if we had just pure capacitance, for instance, then this triangle would be down here somewhere. And the impedance is still going to be the length of that vector. The only difference is going to be this phase angle, which we usually represent as something that looks like that. How you doing, Bill?
No, I'm right here.
Okay, no problem so far.
No, that's some dogs barking in the background, so I had to go on mute.
Oh, okay.
Robert, this is Smokey. I joined about 20 minutes ago. Sorry, I was late.
Okay. Yeah, I wondered what happened to you.
Overslept.
Any questions?
No, I'm good so far. Hanging in.
Okay. All right, we want to talk about resonant circuits. So if we take an inductor and a capacitor and we put them in series or parallel, we call it a resonant or a tank or a tuned circuit. And it's because it can act as an electrical resonator, sort of the equivalent of a bell or a tuning fork, that's going to oscillate at some fixed frequency. And that frequency will be determined by the values of the inductance and the capacitance. And it turns out that the resonant frequency is going to be whatever frequency that the inductive reactance and the capacitive reactance are equal to one another. And they basically cancel each other out. So all we have left is whatever the pure resistance is in the circuit. And what's actually happening is when you apply some energy to that resonant circuit, as you charge up the capacitor, it's going to store that energy in the electric field until it's full, basically, so there's no more current flow, at which point it starts to transfer the energy to the inductor, where it's going to start charging up a magnetic field until it's full, So all we're gonna do is move the energy back and forth between the inductor and the capacitor. If there were no losses or no resistance, it would just go back and forth forever and be resonant. Because in the real world, there's some resistance. We have to keep adding a little energy to make up for what's lost to keep it resonating. Just like when you hit the tuning fork, if it was a perfect tuning fork and there were no resistance in the metal, it would ring forever, but it doesn't. Because every time the energy moves back and forth, you lose a little bit of it through the resistance, and it gets converted to heat or sound or some other form of energy, because it never actually goes away. We just move it around. So the basic thing is that resonance is when the frequency at which the capacitive and inductive reactances are equal, and the total impedance will be purely R, or resistive. So the formula is 1 over 2 pi times the square root of the product of LC. And here I showed how you get there, because we say that X sub L is equal to X sub C for resonance. So if you follow through these, I just manipulated the equation to find F, okay, which is how you get it back to 1 over 2 pi square root of LC. So it's, again, just simple algebra, except you have to do a square on the square root. And this little animation is showing the energy going back and forth between a magnetic field and electrostatic field. So this was just an example. If I had a 1 microhenry inductor and a 1 microfarad capacitor, what would the resonant frequency be? So if you plug those into the formula, you come out with basically 160 kilohertz, which is a number that pops up a lot, but I'm not sure what's important about it.
I don't know, I forget.
Okay, so we can have series or parallel resonant circuits. The resonant frequency is the same. It doesn't matter if you put them in parallel or series. The behavior is different. So for a series resonant circuit, and I plotted this circuit down here. So we have frequency along the horizontal axis. Okay, as the frequency approaches the resonant frequency, we're going to see the voltage on the series resonant circuit essentially go to 0. And then as we go higher in frequency, it goes back up to whatever the initial voltage was. In this case, we were applying, I think, 1 volt. Can't quite read that. At the same time, the gold or yellow is the current. And you're going to see that at resonance, the current, okay, is at maximum. And if we look at the impedance plot, which is the ratio of the voltage to the current, we're going to see that the impedance goes down to 0. And turns out this is not a very high Q circuit, so that's why it's kind of broad. But it's essentially 0 at the resonant point.
Well, it should be 1 ohm.
Huh?
1 ohm, right?
Well, I said it doesn't essentially. I think this is 1. I can't blow it up, but you're right. Depending on where I measured that. I think I actually did it at between these 2 points, so the 1 ohm wouldn't show up.
Oh,
But you're right. Okay, if it's a parallel circuit, And we plot the voltage and the current, okay? When we get to resonance, the voltage is going to go from essentially 0 up to its maximum. And the current is going to be going from a high current, because at lower frequencies below resonance, this inductor has very low opposition to current flow. So the current goes to approximately 0, or its lowest point at resonance. So again, if you look at the ratio of which is impedance, voltage to current, you can see how the impedance approaches infinity. That's the basic difference between a parallel and a resonant circuit, is that it's a parallel and series resonant circuit. Series resonant circuits have essentially 0 impedance at resonance. Parallel has infinite impedance at resonance. Now, in the real world, it doesn't ever get to infinity or 0. But that's the important thing to remember about parallel and resonant circuits. And I believe there's some test questions about whether it's low impedance or high impedance, depending on whether it's series or parallel. So, what's the resonant frequency of a 1 microfarad capacitor and a 1 microhenry inductor? And we go do that, and we come up with that same old 159 kilohertz. I went through and calculated the inductive and capacitive reactance for those same values and frequency. And amazingly, they both are equal, and in this case, 1.
That's where the 159 comes up.
But it only comes out to 1 if you use the 0.235.
Yeah,
Otherwise, you get 0.99 and
Yeah.
1 point something.
rounding.
Right. So the main things to remember is impedance is the opposition to AC current flow. The magnitude of the impedance is equal to the square root of the sum of the squares of the resistance and reactance. Resonant circuits are either series or parallel LC, may or may not have an R in the circuit. It doesn't really affect the resonant frequency, although I think that's not entirely true. I think it has a small effect.
I mean, it would depend upon,
And that for resonance, capacitive reactance equal to inductive reactance. The formula is 1/2 pi times the square root of LC. And in a series resonant circuit, the impedance is low at resonance. In a parallel circuit, it's high at resonance. So there will be questions about those things. Whether it's a math question or just something like high or low impedance.
we have on every capacitor or every inductor, there's a self-resonant frequency of that.
Well, basically everything.
Yeah.
Because everything has inductance, resistance, and capacitance.
Right.
It's all magic. Okay, inductance. Inductance is a measure of the magnetic field that's being stored. Okay, and it's proportional to the value of inductance, which we do in henries. So when we have a current that's flowing through a conductor, just a straight piece of wire, it's going to generate a magnetic field around the wire, and we usually represent that with the right-hand rule. If you take your thumb and point it in the direction of current flow, then your fingers curl around in the direction of the magnetic field lines around that conductor. So the more current, the stronger the magnetic field, the more field lines you get. And that magnetic field is there as long as there's current flowing. And it's actually storing, even going through a straight wire, it's storing some energy in that magnetic field. Now, just for a straight wire, it's a very small magnetic field, depending on the amount of current. We'll talk about inductors. If you coil that wire, wrap it around something round close together, all those magnetic lines of force tend to concentrate through the center of the coil, and it actually increases the magnetic field. Conversely, if we have a magnetic field and it moves across an conductor, it's going to create a voltage on that conductor, which, depending on the circuit path, can create a current. But it will only create that voltage and current as long as the magnetic field is moving. When the magnetic field stops increasing or decreasing, then the current and the voltage on the conductor goes to zero. Now, also, the current that's going through that conductor is also creating its own magnetic field that's opposing the magnetic field that's causing the current.
That's why the DC motors are proportional to voltage.
Yes, that's why our motors work. And all this is true as long as the magnetic field is moving. So that's the basic reason why transformers don't work at DC. I can apply a DC voltage to the input of a transformer, and I will get a DC voltage and current out one time for a short period of time, and it will decay. So until I change either take the current away or reverse its polarity, okay, I won't get a magnetic field and a current on the output of that transformer. So a transformer turns out to be just two or more. Usually it's just two. Inductors with a common core. It could be air. In the case of like a power transformer, it's usually some special laminated iron that forms the core. It could be ferrite material, which is what you would see in a toroid for like radio frequency transformers, which is how most of those are made today. And the fact that those two or more inductors or coils are sharing the same magnetic field, we call that mutual inductance, where the current going through one is creating a magnetic field, which is creating a current and an opposing magnetic field in the other coil or inductor. We also have a turns ratio in a transformer, which is the ratio of the number of turns on the primary versus the secondary. So if this was a step-up transformer, I would have more turns on the secondary than I would on the primary. If it was a step-down transformer, I have more turns on the primary than I do on the secondary. So the voltage is going to be proportional to the ratio of the turns. So if I had half as many turns on the secondary, the voltage I get out would be half of what was on the primary. Likewise, if I had twice as many, I'm going to get double the voltage out. Now, because transformers have no gain, it just transforms. So if I put a watt into that transformer, the most I can get out is 1 watt. So if I'm getting twice the voltage out, I'm going to have to get half of the current out. Likewise, if I got half the voltage out, I'll get twice the current out. Right?
What's that mean for me?
Okay. Let me see. What's the name? Oh, yeah, this is just showing a typical transformer with a 1-to-2 ratio, and I plotted it. So the gold is the voltage on the secondary, and the blue is the voltage on the primary. And you can see that the primary is, what? Around 12 volts. The secondary, because this is a 2-to-1 step up, should be about 24 volts, and it's just shy of 25. When we look at the current, right, the current on the primary is about 500 milliamps. The current on the secondary is about 250, but it's negative. It's out of phase. Which is an important thing.
Measuring it.
Huh?
That's because the way you were measuring it.
Oh, okay. But remember, the power has to be equal in and out, except for whatever loss there is in the transformer itself. This is just some examples of common. There's a toroidal transformer and just regular coils, the kind of stuff that you see today. I don't have any big power transformers. But let's see if I can do my demo. Well, let me see. Stick it at the end. So if we've got an output, all right, a 10-to-1 turns ratio transformer that's got 120 volts on the primary, what is its output voltage? So if I've got 10 turns on the primary, for every turn on the secondary is going to be what? 1/10 of the primary, or 12 volts, which would be a fairly typical 12-volt transformer that's used for lots of things. In some cases, it could be center tapped, where you get 6 volts out to drive filaments of tubes, which we'll talk about in a little bit. So the main thing to remember is the transformer is 2 or more coils of wire on a common core. Mutual inductance means they share a magnetic field. The turns ratio is the ratio of the primary to the secondary turns of wire. Now, later on, we'll talk about impedance of a transformer, which is the square of the turns ratio. So if I had a turns ratio of 2, the impedance ratio is going to be 4. And that will be when we talk about matching for antennas, basically. So a step-up transformer has a higher voltage on the secondary and a higher current on the primary or lower current on the secondary. And a step down gives you a lower voltage on the secondary. So let's see.
Recording.
Well, I'm still recording. I'm going to let you be the guinea pig.
All right.
Well, not a guinea pig, but the demonstrator. If I can get my other camera to work again, but I had it working. This is a little MIT demonstration of Lenz's law.
Okay. What if he breaks the law?
Oh, I remember this.
What if he breaks the law?
All right. All right. Let me get the camera working here.
These stuck together.
Okay, don't, you could hurt yourself trying to take them apart. Those are super magnets.
Yeah.
Um. Where's? Oh, okay. All right. Oh, I guess I have to stop sharing that one. I'll figure this out sooner or later. Where's my video? I had it working before.
And not start video, build to start the video camera. Please select another video camera. Okay, that's very helpful.
It worked before. What's the end is going to end the Zoom session.
Don't you have a camera on
Do
your,
you,
Yeah, but it's I might have to use that one. But I had this one working.
I always have problems with this shit. Oh, there's a camera. Oh,
Yeah, but that's this one.
well, maybe you have to turn it off first,
Or what?
the internal camera.
It is.
Oh,
The light went out. And it said the camera was off. All right. We'll go back to see if we can use this guy.
what is that red one down there for? Where it says more.
Oh, some
Oh,
chat?
okay.
Oh. Somebody trying to chat? Oh. Be right back. At some point. Okay, so I guess if we,
that's you.
I know. There you go. Are we sharing?
Yep.
Oh, that camera was work. It's on.
Nice beard.
Thank you. I was walking through Sam's the other day and heard someone yelling over by the checkout line, and I turned and looked, and there was a little boy, maybe year and a half, 2 years old. His mother had him in the seat of the cart, and he was waving frantically with a big smile on his face saying, "Hey, Santa, hello, Santa." So I walked over and talked to him, and his mom asked me what Santa was doing at Cleveland, and I said, "Well,
You got it working now.
Yeah,
there we go."
I don't know how. It says it's sharing. You guys see Dan?
Yep, sure can.
Okay,
Yes.
Dan has a piece of PVC about 2 feet long and a piece of copper pipe 2 feet long. And in his other hand, he has a super duper magnet
Big magnet right
that I
there.
got from the Magnet Bros. It's a strong enough magnet, and there's 2 of them there together. You could definitely draw blood trying to take them apart. Trust me. So the first thing, he's going to show you that the magnet has no effect on that PVC pipe. And then you're going to drop it. And we're going to see how long it takes. It should be approximately a 1/16 of a second if gravity goes at 32 feet per second squared, right? So when I start to count, 1,000 and,
Okay.
oh, now 1,001. Okay. Pretty quick.
Yeah, pretty quick.
All right. Now, it shouldn't have any effect on the copper. Copper is a good conductor. It's almost as good as silver, but it's not magnetic. So we'll do the same thing and we'll time it. Go. 1,001, 1,002, 1,003, 1,004.
That
Okay.
was slick.
Why did that happen?
I have no idea.
Sure you do. It's called Lenz's law. Okay. We have a conductor.
Mhm.
It's a coil. It's a 1-turn coil,
Right,
right? Happen to be long,
right.
but it's a 1-turn coil. We have a magnetic field that was moving. What happens when we move a magnetic field across a conductor? It creates a voltage and a current
Okay.
and an opposing magnetic field. So that's what slows it down is the opposing magnetic field. Okay.
And it's warm too when it comes out of there.
Well, there's some energy being moved around.
Yeah.
Okay. Well, you didn't believe us?
I just wanted to see how.
That's a good. That's a good demo. I like that.
That is good. Those are
So-
pretty good magnets.
Depending on the resistance and how much energy is lost would determine how fast or slow the magnet falls. I mean, if it was a strong enough magnet and a low enough resistance, it would almost be stationary. Like that. Okay. So.
Want me to put this over next to your hard drive?
Question.
It's a solid state.
Question.
Go ahead.